Good morning, everyone. I'm Qingguo, the second author of this talk, and I'm representing the first author, Jianan Li. Today, the topic is reversible nanoscale control of the charge neutrality point in graphene using lanthanum aluminate strongly tightened heterostructures. As we know, 2D material and 2D system has attracted a lot of attention in the recent years because of their unique physical properties. Here is a list of 2D materials and 2D systems, and the list is still growing every year. In our group, we are mainly focused on the lanthanum aluminate strongly tightened heterostructure. Lanthanum aluminate strongly tightened, which we call them shortly for LaAlO3, they are both wide band insulators. But when we put these two materials together, a 2D electron gas can be formed when the thickness of LaO is above 4 unit cell. And we can use the conductive VFM lithography technique invented by our group. We're able to write conducting nanostructures at the LaO3 interface. So when we put positive voltage to the tip, we can write conducting nanostructures. But when we put negative voltage to the tip, we are able to erase the nanostructures we wrote. So it's a reversible process. The width of the nanostructure is around 2 nanometers. It's very close to the size of the tip. With this powerful tool, we can create many types of nanostructures by AFM sketching, such as single electron transistors. As we know that the system is so clean, we can even do ballistic transport up to micrometer scale. We can even create waveguide for electrons and Cooper pairs. In 2012, we also found electrons can pair without superconductivity in this system. In our earlier attempt, we have shown that combine these two systems can show some really interesting results. In this case, we patterned graphene onto LaO3 interface and saw graphene is a really great gating material. And in the other experiment, we observed this room temperature quantum transport signature. Since the STO have very high dielectric constant, it can share the backgate very well. The weak anti-localization signature will show even up to the room temperature. So lanthanum aluminate strongly tightened is a pretty good substrate for graphene experiment. Our goal is to combine these two systems together. Initially, we're using the PMMA to transfer the graphene, but however, we found it will leave a lot of residue on top of LaO surface after the transferring and patterning. Besides, LaO3 is not writable anymore after using the PMMA as a transferring layer. Fortunately, we found a replacement for PMMA, which is called high flow. So it's chemically inert and nonpolar material. It is only solvable in FC40, but not in water, acetone, IPA, and etc. So we use this polymer to transfer the graphene onto LaO3. We are using the wet transferring method and then do the photolithography. At the final step, we added one more step to clean the surface of the graphene LaO3. So we did AFM contact mode scan to sweep away some of the residue, and then we did the room temperature STM. So we show that even at atomic scale, our graphene is still clean. So here is the transport data at 2 Kelvin. We can see clearly this quantized Landau level. The mobility of the graphene is about 10,000 at 2 Kelvin. we do care about whether the graphene is still the LaAlO3 interface is still writable with graphene on top of it. The usual way to test the writability is to do PFM. So here we wrote two funnels and one nanowire that go across the graphene region. After the writing, we did the piezoelectric force microscopy, and and it shows here that the nanowire is at exactly the same location as we designed. And also, we observed the conductance jump between these two electrodes. So we can successfully write the nanostructure with graphene on top of it. With this powerful tool, we are able to do AFM lithography on the graphene LaSTO system. So here we wrote a rectangular region with positive voltage applied to the AFM tip, and it's covering only half of the graphene. So here is the four terminal conductance of the device resistance during writing. So we can see that it is the resistance of the graphene is changing as the time goes by. So we're actually doping the graphene during the writing process, and our graphene is becoming more and more n-typed after the writing. This is the room temperature data, and after we cool it down to 2 Kelvin, we can see a clear peak splitting and at low magnetic field. So since this is the two terminal measurement, one peak is corresponding to the main channel of the graphene, and the other peak is corresponding to the written region of the graphene. So we can clearly see that the direct point is at different location. So we are actually doping the graphene in the written region. And then we did the Hall measurement of these two different regions on the left and on the right. And we measured the Hall resistance and then calculated carrier density, so we can clearly see the difference between these two, the patterned and unpatterned region. So in our sample, the carrier density difference on the two sides, like the left side and right side, is enough to keep them at adjacent lambda level filling factors. And when we sweep the baggage from negative 10 volts to the positive 10 volts, the carrier density type in these two regions might transit from unipolar to bipolar and then unipolar again. And in the bipolar region, the mixing of the edge state will produce a quantized conductance at 3e square over h over 3e square. So we observe this unusual quantized conductance on graphene due to the p-n junction we created on the LaSTO. When the magnetic field is reversed, the quantization of the R1 and R2 got switched because of the reversing of the current direction. For short summary, we can write nanostructures on the LaSTO interface. And we use Hyphalon to replace PMMA so that writability of LaSTO interface is preserved. The nanostructures we wrote on LaSTO can be imaged by the piezoelectric force microscopy. The carrier density of graphene can be locally tuned with this by this writing process, and we can create p-n junctions. Besides, we observed the unusual quantized conductance due to this p-n junction. Thank you.